everyone. Next topic is computing with complete binary tree. Computing with a complete binary tree is a binary tree in which all levels are filled except the last level, and it filled from left to right. Also, the height of the binary tree is bounded by big O of log n is nothing but the number of element in the tree. Parallel algorithms use this property of the binary tree to solve the problem with the input size till n. Number of parallel algorithms are designed using for complete binary tree. In the example of 8.3.1 complete binary tree, first finding the sum of the product of n integers, after that generation of prefix code, and next one is parallel matrix multiplication. Okay, suppose consider a problem with input size n and assign all data at the leaves of a complete binary tree. Okay, and necessary computations on these data items in a parallel way and obtain partial result of these computations at the non-leaf node. After that, applying a bottom-up approach, combine the partial result and reach the root node of the complete binary tree with the big O of log n times. Okay. Now, algorithm for sum of integer using complete binary tree. In this algorithm, let's n equal to 2 raised to k and k less than 0 be the input size of the problem. In that, assign n integers to be added at the leaves of a complete binary tree. After that, addition of all leaf nodes concurrently and store partial result of the additions at the respective internal nodes. Continue the same step until all partial results are combined at the big of nth step, and final you have to find sum of n integers is obtained at the root node. Okay, sum of n integers is obtained at the root node. Got it? Now next one is complexity analysis. What is the complexity analysis when you have to finding sum of n integers using binary tree? In that, the parallel algorithm with a complete binary tree is to be compute the sum of n integers require the maximum number, okay, of n by 2 processors working in same parallel way, and all parallel computation must be synchronized, and all concurrent addition for a specific value should be completed before concurrent addition for the next value to be find out. Okay, now height of complete binary tree with the element is bounded by big O of log n times. In parallel algorithm with a complete binary tree, perform big O of log n rounds for the for loop of I. In each trip round for loop of I. In each trip round for the for loop of I, each processor access the memory twice. Processor access the memory for the twice. First one is read two operands to add. And second one is store the sum of those two operand. First one is you have to read, and second one is store the sum of these two operand. Is that each processor is assumed to take a constant time to calculate the sum of two operands. Okay, to calculate the sum of two operands. After that, all the processor partially perform the addition and the constant time is needed for each trip round for loop of n of I. Okay. So the total time therefore the total time required for the big O of n, total time required for the big O of n, time complexity is big O of n trips round for loop of I. Okay, this is the time complexity. Now we will solve example. First one, find out the sum of the following 8 integers using parallel algorithm with a complete binary tree. Okay, in the diagram of 8.3.1, we have to assign given element in an array at the leaves of a complete binary tree. Okay, in that 8, 6, 12, 9, 4, this is the input size data. After that, in figure 8.3.1, we have to take addition of leaf nodes partially to get partial result. Okay, addition of leaf node partially to get a partial node. It means in that 8 plus 6 is 14, addition of this leaf node, and partially result is placed in fifth, partially result is count 15. Okay, and combine those result in the topmost approach. In that, combine this result 15 plus 21 is nothing but 35, and combine this result at the bottom up approach. 35 is combined at the bottom up approach, it's 77. Okay, fine, and get final result at the root of the complete binary tree, and final result is 77. Okay, it means 8 plus 6 14, 12 plus 9 21, and 40 partial result is 14 plus 21. Now 14 plus 21 is 35. Now this is 35 partial result. In next 4 plus 16 is 20, then 10 plus 12 is 22, then partial result addition 20 plus 22 42, and final partial result is 35 plus 42 is 77. It is a final result and it is placed at the bottom up approach. Okay, got it this example? Now next example. Calculate the product of the following 8 integers using parallel algorithm with a complete binary tree. Okay. In that, in figure 8.3.2, we assign given element in an array at the leaves of a complete binary tree. Okay. And in figure 8.3.2, is that we perform the multiplication of leaf node parallelly to get partial product. Here in last example, we perform addition operation, and in this example we have to perform multiplication operation. In that 5 into 12 100, after that partial result added, it is nothing but the combine this partial result in the bottom up approach and to get the final result at the root of a complete binary tree. Okay, got it this example? Now next, these are the university questions. First one is, explain how parallel computing are possible using complete binary tree. In that you have to explain in detail algorithm of parallel computing, then also one example, etc. Now these are the examples of parallel computing with the complete binary tree. Thank you so much for watching this video.